Can the laws of gravity be broken? People have pondered the natural rules that govern the cosmos ever since Isaac Newton was struck in the head by an apple that fell from a tree above him. Why do objects fall from trees, and sometimes even land on people's heads? Welcome to the channel, subscribe and let's dive in. The gravitational force is by far the least powerful of the four natural forces. Lifting anything into the air is all it takes to overcome gravity. It takes a remarkable amount of effort to resist gravity's persistent nature and boundless range, which is what makes it so bothersome. Even if gravity were 1 billion times stronger than it currently is, it would still rank last among all the forces due to its extreme weakness. You're being pulled by the entire mass of the Earth, yet you can defy its full gravitational power by reaching across and grabbing a pencil. There will inevitably come a point where you'll fatigue and put down the pencil, but there are other ways to magically defy gravity. When things go up, they must come down. To put it simply, according to Newton's 3 principles of motion, which are the basis for understanding gravity on Earth, we now understand that each object in a 2-particle system exerts an equal and opposite force on the other object over the square of the distance between the particles. This force is equal to the gravitational constant times the masses of the 2 objects. The relationship between force, mass and acceleration is what causes the apple to fall to the Earth. Since the 2 forces are equal, the Earth's large mass causes it to accelerate relatively slowly towards the apple, while the apple's tiny mass causes it to accelerate rapidly towards the Earth. But the real question is, can people genuinely defy gravity? The short answer is no, and it has been proven experimentally both on Earth and in outer space. No matter how little, every particle in the cosmos is theoretically capable of exerting a force on every other particle. However, because the strength of all other gravitational forces on an apple is so negligible, they're frequently disregarded. Yes, mankind have successfully defied gravity on numerous space missions throughout the years, and if one's definition of defeat is as simple as escaping the Earth's atmosphere and floating in space, they are not actually defying gravity, despite the fact that they are floating in a weightless environment. With what we know right now, it's just not possible. The ability to defy gravity seems to be a test of human ingenuity, resourcefulness and cunning. Since the Higgs boson was recently discovered, scientists have been attempting to understand how particles acquire mass. Given the connection between mass and gravity, does the Higgs boson hold the key to understanding the origins of gravitational fields? Through their investigation of the particle, researchers expect to gain more knowledge about gravity and mass in the years to come. Although it is, as far as we're aware, impossible, defying gravity nonetheless inspires and fulfills human dreams. Who hasn't gazed up at the stars at night and wished they could take off and explore the wonders of the cosmos? Defying gravity in space. The magnetic force is a powerful phenomenon that can be observed in everyday life. For instance, magnets can be used to hold objects on the side of your fridge for an indefinite period, showcasing the power of magnetic attraction. Additionally, the use of superconductors in creating stronger magnets has allowed for levitation of entire train cars, creating high-speed transportation that floats above the track. While it may seem that escaping the Earth's gravitational pull and entering space is an easy feat, gravity is a formidable force that must be overcome. Even at the edge of the atmosphere, where space begins, Earth's gravitational pull is still strong. Therefore, to remain in space, one must continuously accelerate to counteract the force of gravity. A significant amount of energy is required to keep a spacecraft in orbit. Thus, most of the energy expended during a rocket launch is not used to reach space, but to stay in orbit. To break free from Earth's gravitational pull altogether, a speed of at least 11.2 kilometers per second, that's 7 miles per second, which is around 33 times the speed of sound, must be achieved. Numerous techniques such as magnetic levitation, acoustic levitation, and even quantum levitation can be used to achieve levitation. By using the strong magnetic force to defy gravity, magnetic levitation enables items to float in mid-air. On the other hand, acoustic levitation employs sound waves to produce a standing wave pattern that can lift small objects into the air. Quantum levitation, however, may be the most bizarre type of levitation. When a superconductor is exposed to a strong magnetic field, it's locked in a state of magnetic flux, which causes this phenomena to happen. The end result is a substance that appears to defy the rules of physics by floating smoothly above a magnetic surface. From suspending a small laboratory-scale stationary object to a large-scale mobile applications like maglev vehicles capable of carrying people and materials up to speeds of several hundreds miles an hour, magnetic levitation has come to be used in a wide variety of contexts. The configuration of the system, as well as which parts should be fixed on the guideway and which should be mounted on the vehicle, must be decided by the designers of the maglev system. Maglev trains and high-speed rail have become realities. Maglev, also known as magnetic levitation, has the potential to achieve for the GIR what airplanes did for 2IR in the 20th century. High-speed rail train systems have been created and put into use in the majority of Asian and European nations, but GIR trains like China are constructing maglev or floating high-speed train systems. In place of the outdated steel wheel and track arrangement, maglev train systems levitate the trains over a guideway using strong electromagnets. The trains are suspended, guided and propelled by a system known as electromagnetic suspension, which uses a huge number of magnets to create regulated tension for lift and propulsion along a track. Maglev trains outperform conventional ones in terms of speed, quietness and smoothness. After World War II, German Transrapid International invented these based on a 1934 patent. The quickest intercity maglev rail line in commercial operation in the world, the Shanghai maglev train connects the city's subway system to the Pudong International Airport. The Chinese began a new project in 2010 to extend the line to Hangzhou, which is roughly 105 miles distant. Work is expected to be finished in 2014. The train could cover the distance in 27 minutes at the anticipated speed of more than 200 miles an hour. Due to their convenience, effectiveness and advantages for the environment, the Chinese are planning to build identical maglev trains all around the nation. Small things can be raised in the air by using sound waves as an invisible pair of tweezers. Researchers from the University of Technology, Sydney and the University of New South Wales have recently shown that it's necessary to consider both shape of the particle and how this affects the acoustic field in order to precisely control the particle using ultrasonic waves. When sound waves interact, a standing wave is created with nodes that can trap a particle. This phenomenon is known as sound levitation. The fundamental mathematical theory for acoustic levitation developed by Gorkov is that the particle being trapped is spherical. Asymmetry, however, alters the force and torque applied to an object during levitation and shifts the site of the trapping according to studies. To properly manipulate or classify items smaller than an ultrasonic wavelength, the Biogenic Dynamics Lab has created a model based on shape and geometry. The two emerging domains of non-contact ultrasonic manipulation and metamaterials, materials designed to have a property not present in nature, will become more intertwined as a result of this paradigm. The Biogenic Dynamics Lab's associate professor, Sebastian Oberst, said that by being able to precisely control tiny objects without having to touch them, scientists may be able to investigate the dynamic material properties of delicate biological objects like insect appendages, insect wings, ants and termite legs. In order to create and innovate hypersensitive vibration sensors, the scientific community has concentrated on attempting to understand the mechanical characteristics of termite sense organs. The most far-reaching application of this present theoretical research is employing non-contact analysis to extract new material principles for creating unique acoustic materials, because it's currently difficult to evaluate the dynamic features of these biological materials. Levitation may appear to be pure magic, but it's actually made possible by science's amazing power and our knowledge of nature's basic rules. Who knows what fantastic levitation and anti-gravity technology feats we may accomplish in the future with ongoing study and development? Thank you for watching, and follow for more.